All right, let's take a look at water. Water is a ubiquitous substance on Earth, right? We find it everywhere and we need it to be alive. So, yeah, we're gonna encounter it and deal with it pretty much on a daily basis. And in chemistry, at least in this level of chemistry, we use water a lot. Now, the one thing about water that we haven't discussed yet, but it's an important factor that we're gonna exploit in not only this lecture but future lectures as well, is the fact that water is one of the substances that has a dual activity. On the one hand, it does have H pluses to give away, in which case it does behave like an acidic substance, but on the other hand, it does have lone pairs on the oxygen, meaning that it can behave as a base. And if you have simply pure water, some of the water molecules can start behaving acidically, and other ones can behave basically, meaning that one of the water molecules will be taking up an extra H plus, the other one will be giving away an H plus, and in the process of that happening, you produce hydronium and hydroxide. Now, the extent to which this happens is actually very small. In fact, at room temperature, for pure water, you only have about 0.1 micromolar concentration of either hydronium and hydroxide. So most of the water remains neutral, H2O. But some small extent, technically 1/10 of a part in million, will actually turn into hydronium and hydroxide. If you apply the idea of the equilibrium constant to this, right? Water plus water, both of those are liquids, so you don't apply it to the equilibrium expression. But if you apply the hydronium, which is AQ, and the hydroxide is AQ, your equilibrium expression, which we're calling KW to make it obvious that this is the auto-ionization of water, is simply the product of the hydronium concentration times the hydroxide. At room temperature, that happens to be 10 to the negative 14 because 10 to the negative 7 times 10 to the negative 7 is 10 to the negative 14. Now here you could also use a logarithmic relationship, and this kind of like links up the idea of the pH and pOH as I had before. You could take the negative log of both sides, for instance, right? And if you take the negative log, this is regular log, not natural, but regular log. Negative log of 10 to negative 14 is actually 14. But when you have the negative log of hydronium times hydroxide, whenever you have multiplications inside logs, you can write this as the summation of individual logs. And because you have the negative in front of it, the negative gets distributed to the summation. So what you have right here is pKw equals pH plus pOH. And this is a relationship that we will also use in future lectures, right? So the pH plus the pOH in essence equal 14. That's an equation that you probably want to remember. It's a relationship that we're definitely going to use in future lectures. All right, so just to give you an idea, and this is something you may have done in previous chemistry classes or prior chemistry classes. We can use either the idea of the Kw equating to the product of hydronium times hydroxide concentrations, or we could use the idea that the pH plus the pOH equals 14 to basically solve for either or concentration. Okay, now the other thing too is that pure water, which auto-ionizes into 10 to negative 7 molar concentration of hydronium and 10 to negative 7 molar concentration of hydroxide, automatically has a pH of 7. And this is what we refer to as being neutral pH, because the amount of acid is equal to the amount of hydroxide, so they cannot cancel out in essence. But let's say that the amounts were different, right? So let's say that you actually have more acid than you do have base. By default, this solution will be regarded as being acidic. But when you take the negative log of 2 times 10 to the negative 7, you find out that the pH is now 6.69, less than 7. But the solution is acidic because you have more hydronium than you do have hydroxide. To give you a much more drastic example, if the concentration of hydronium is 3 times 10 to the negative 2 and the concentration of hydroxide is 3 times 10 to the negative 13, mind you, the product of these two numbers still has to equal 10 to the negative 14. So increasing one of the values automatically will decrease the other one, and vice versa. But taking the negative log of 3 times 10 to the negative 2 yields a pH value of 1.52. And what you're seeing right here is that as you do increase the concentration of the acid, the pH drops. The pH becomes smaller and smaller. And on the other hand, if you increase instead the hydroxide concentration, then the pH starts increasing. In fact, it will increase above a value of 7. So acidic solutions are regarded as those that have a pH less than 7, whereas basic solutions are those that are regarded as having a pH greater than 7, and of course a pH equal to 7 is considered to be neutral. So the scale, roughly speaking, at least for water, in terms of the pH, goes from 0 to 14. Not to say that we're not going to see some things that have pHs that are negative. That can actually happen, especially if the acid that you're dealing with is highly concentrated and strong. That can actually happen. But generally speaking, for most things, the pH is going to lie between 0 and 14. Okay, so let's take a look at the Ka expression. Now, this is a very specific equilibrium expression, one that involves an acid reacting with water. And the idea that you have to keep in mind is that the acid is going to give away an H+, and the substance that it reacts with will have to be a base, right? So if HA is an acid, water has no choice but to be a base. So HA will give away its H+, it'll become A-, water will acquire an extra H, so it'll become H3O+. So the total number of H's remains constant on both sides, but notice that we went from being neutral to now having charges as a result of exchanging that H+. Now, if you were to write the equilibrium concentration, and I'm actually gonna kind of break my definition a little bit. I'm going to include the value of water, and I have a purpose for doing that, as you're going to find out in the expression. Now, the amount of water, the concentration of water, as we have discussed in the equilibrium lecture series, the concentration of water is very large. So much so that whatever is happening within it, even if water is one of the reactants or products of the reaction, the change in concentration is very insignificant compared to the actual concentration of water. So what that means is that you could multiply the quote-unquote equilibrium constant by the concentration of water, which is 55.5 molar, and this multiplication, the true K equilibrium times the water concentration, is what we call the Ka, the equilibrium constant for the acids. And specifically, what you can see, this is the A- times the hydronium, which are the products here, divided by the acid, right? So that's the equilibrium expression for Ka, for the acid dissociation in water. And the value of Ka can take quite a bit of ranges. For the strong acids, the value of Ka is not only greater than 1, but in some cases is a lot greater than 1, meaning that these things really want to give away that H, meaning that they're strong acids. But then you have a bunch of other ones that have values of Ka less than 1, implying that the equilibrium of these particular acids lies in simply the identity of the acid itself. Some of it will dissociate to give you H+, but it's not going to be product favor. Most of it will remain intact, as is depicted right here in the table. So as you increase the value of the equilibrium constant, the Ka constant, the acid becomes stronger. The strong acids already highlighted are the ones that have, in general, values greater than 1 for the equilibrium constant. Water itself, if you look at this thing, water is the substance that has, at least in this table, that has the equilibrium constant with the smallest value. So everything else that you see here is acidic from the point of view of water, right? So you add any of these substances, you expect them to be acidic, at least from the point of view of water. All right, now another thing that we can do is use the equilibrium expression for the acid dissociation, right? So you have A- times hydronium divided by HA being equal to Ka. We could use that to solve for the equilibrium concentrations of all of these species. The one that probably would be the most important is the concentration, the equilibrium concentration of hydronium, which then can be used to find the pH. Now, another thing that I want to also introduce is that because the P function is just the negative log of whatever, if you take the negative log of Ka, you are dealing with something that we call the pKa. Once again, Ka is the variable, right? The same way that the variable could have been H+, or it could have been OH-. Now we have Kw, Ka, and in a little bit we'll have Kv as well. But the negative log of something is going to be the P of that very something. Alright, so if you actually take the negative log of the K values, you get some numbers that are a lot easier to digest and a lot easier to look at, right? So instead of having all those exponential values, now you have numbers that range from like 0 to 20, roughly speaking. So a few things to notice. First of all, the strong assets, if you look at them from the point of view of pKa values, the strong assets, generally speaking, have negative pKa values. So not only are they small, they are already in the negative scale. So having that negative value tells you, yeah, this is a strong asset for sure. On the other hand, the value of the pKa increases as the asset becomes weaker and weaker, right? So decreasing the pKa tells you that you are dealing with a stronger asset. And one more thing, notice water. The pKa of water is 15.7, not 14, right? The Kw is equal to 14, but the Ka of water is actually 15.7. And that's kind of an interesting little nugget of information because for the longest time, I personally, as I was a student, used to think that the Kw and the Ka of water were the same thing, but they are not. And the reason they're not is because when you write the auto-ionization equation for water, right, water plus water gives you hydronium and hydroxide. The Kw is simply the hydroxide concentration times the hydronium concentration, which equals 10 to the negative 14. But the true equilibrium expression for this, if we actually do include the waters, which typically we don't, but I'm going somewhere with this, as you'll find out. If we do include the waters, then we will have water, the concentration of water square on the denominator. The Kw in essence is the true equilibrium constant multiplied by the concentration of water squared. That's what the Kw is. But the concentration of water to the first power multiplied by the equilibrium constant is what we call the Ka. So we're actually basically off between the Kw and the Ka value by a factor of 55.5. Alright, so in essence, the Ka for water is hydronium times hydroxide divided by the concentration of water, which is the same thing as saying Kw has to be divided by the concentration of water. And if we do that, right, we already found out that the concentration of water, if you do the calculation, as I'm kind of like fast passing right here, is overall 55.5 molar. If you divide the Kw by the 55.5 molar, we end up finding out that the Ka has a value of 1.8 times 10 to the negative 16. And if you take the negative log of that number, you find out that the pKa of water is 15.7, exactly what the table tells us. Generally, textbooks, especially Gen Chem books, general chemistry books, they don't tell you this. They kind of just bypass it. They'll give you the table, granted, and the value will be there, but they don't say anything about it. And that used to bug the heck out of me. So I'm kind of going out of my way to show you why the pKa value for water is different than the pKw value, right? They're related terms, but they're not exactly the same thing. All right, now let's take a look at the bases. The bases have a similar approach in that you're now looking at the reaction between a base and water. And the bases take up H pluses. So when you react a base with water, one of the H pluses of water will go with the base. So now you make HA. And the water, which has lost that H plus, has become now hydroxide. This is the typical base dissociation equilibrium reaction, which is denominated as Kb. And for bases, it's the same idea. There's a bunch of bases. And notice that most of the ones that I'm showing here have nitrogen within them, because nitrogen usually will have lone pairs available and present for it. All of these bases have Kb values that are less than 1, meaning that they're weak bases. But as you do increase the value of the Kb, you increase the strength of the base. All right, and okay, so here we're showing the acid again. I'm kind of going to show you something in regards to it. So for the Ka equations, Ha plus water turning into A minus and hydronium, you have the Ka expression, right? For the base dissociation equations, you have A minus plus water turning into Ha plus hydroxide. So the Kb expression is Ha times hydroxide over A minus. And we also know that the auto-dissociation equation of water, water plus water, gives you hydronium and hydroxide. And check this out. Technically speaking, I'm putting that little line right there, the pink line, because if you were to add the equation for the dissociation of acids with the dissociation of base, the HAs cancel out, the A minus cancel out, and you end up with two waters on the reactant side yielding H plus and hydroxide on the product side. So in essence, we are adding the acid dissociation with the base dissociation equation to yield the KW equation, which is hydronium times hydroxide. So yeah, so you cancel out all that stuff. Now take a look at this. This is kind of interesting. If you input everything that you have in here, right? So I'm not canceling out the HAs and A minus just yet. I'm actually just writing everything out, but you know they obviously cancel out in the equation, right? You will have A minus on top, hydronium on top, based on what's here in blue, HA on top, hydroxide on top. You'll have your HA on the bottom and your A minus on the bottom. And right now I'm not including the waters, which are liquids, right? So what you can see is that here I color coded it quite nicely. You have A minus times hydronium over HA. Well, that's actually the Ka expression. And over here you have HA times hydroxide divided by A minus. That's the Kb expression. So quite simply stated, Kw equals Ka times Kb. This is an expression that you might actually use in the future to solve some problems. All right, now another thing that is important to say in regards to that, right? This is actually a relationship that we're going to use when dealing with titrations. This expression allows you to switch over from Ka to Kb or from Kb to Ka. And an example of that is what I have here for piperidine. Piperidine is a base, and we know it's a base because we have a value of Kb for it, right? That kind of gives it away that this is a base. But if we look at the substance that is its direct acidic counterpart, the conjugate acid of it, the only difference is that this will have an extra H plus, right? So instead of having just the H, you have the H2 plus for it. This is known as piperidinium, and it's the acidic version of piperidine. So this ought to have a Ka value, and the way you find out the Ka value is you simply divide the Kb value from Kw. So you have 10 to the negative 14 divided by the 1.33 times 10 to the negative 3 Kb value, and automatically this gives you the Ka value for the direct conjugate acid of this base. Yeah, so these two relationships are kind of related to each other. Kw is equal to hydronium times hydroxide, but it's also equal to Ka times Kb. So you can kind of see the correlation happening for the two expressions. And if you take the negative log of both sides, ultimately you end up with the following relationship, that 14 equals pH plus POH, but 14 also equals pKa plus pKb. So these are different expressions that we're going to use at different times, and you'll see the use and utility in future lectures. All right, yeah, so the pKb, much like the pKa, as it decreases, you end up dealing with stronger bases in general, right? Alright, so I'm going to stop the video right here, and in the next video we're going to talk about trends, and eventually we're going to do some calculations. So I will see you in the next video.